My name is Cindy Briere, and I'm the Deputy Director for the SLOSH Center. This position affords me the pleasure to work with our wonderful scientists like our guest speaker today. I'm delighted to have you attend our CPAESS Discovery Seminar Series. CPAESS scientists do everything from explore our ocean depths to fly into hurricanes, heliophysics modeling, and those that unravel the mysteries of the Arctic. And we want to share the science with the public, the NCAR, UCAR communities, and our many colleagues at universities and agencies across the globe. Just to orientate you, we are going to use Slido for questions, and you can post questions for our speaker throughout the seminar. The questions will be addressed at the end of the seminar. You will be able to find the Access tab at the top left of your screen. Today, it is my sincere pleasure to introduce you to Dr. Andrew Penny. Andrew is a CPAESS scientist in the Storm Surge Unit at the National Hurricane Center. Andrew leads research and development efforts related to advancing the capabilities of the probabilistic guidance used for operational storm surge forecasting. More specifically, his work involves making improvements to the atmospheric forcing used in the storm surge model and testing new methods for addressing meteorological uncertainty within the ensemble modeling system. He also develops and manages the data flow for real-time experimental guidance products. Today, Andy will share his recent work with you in a seminar entitled Improvements to the Wind Flow Used in the Operational Storm Surge Model at the National Hurricane Center. Please join me in welcoming Andrew. Over to you, Andy.
Well, thanks for the introduction, Cindy. Appreciate that. Let's see here. Okay. Yeah, so today I'm going to be talking about some recent work that we've been doing to try to improve the wind field that we use for operational storm surge modeling at the National Hurricane Center. First of all, I'd like to thank the team we have in the Storm Surge Unit at the National Hurricane Center, as well as a few other folks that have helped with this project over the last few years. So just to start, I'm going to provide a little bit of an agenda of what today's talk is going to entail. So first of all, I'd like to provide some background information and just to provide motivation for why these types of improvements are necessary and important. And I'm going to be talking about some work we did to try to improve the storm size in the operational model that we use in the probabilistic storm surge model. And I'll show some verification with that. Then I'll talk about more recent work to try to improve the wind field structure. So kind of beyond the radius of maximum winds in the outer wind field. And I'll show some verification of some hindcasts, deterministic hindcasts to go with that. And then talk briefly about work to try to adapt this new wind model that we're looking at into the probabilistic guidance. And then I'll provide a few summary and conclusions. So I think, in terms of looking at improvements to the guidance, it's important to understand the context in which NHC operates. And so I thought I would just kind of revisit their mission statement. And I'll read it here, just the first line of it. It says, the NHC's mission is to save lives, mitigate property loss, and improve economic efficiency by issuing the best watches, warnings, forecasts, and analyses of hazardous tropical weather, and by increasing understanding of these hazards. So in the Storm Surge Unit, we have 3 public-facing products or graphics that we use to communicate the hazards and risks associated with storm surge. They all have different audiences and different, slightly different uses, and but I'll just kind of highlight these here. On the left is the Storm Surge Watch Warning graphic. This highlights areas that are at risk to life-threatening storm surge. The watch is defined as the possibility of life-threatening inundation within 48 hours, and a warning is the danger of life-threatening inundation within 36 hours. And this graphic is aimed at the general public. That would be the intended audience. It can be used for evacuation purposes. And it's probably our most important tool towards communicating the risks associated with storm surge. The middle panel here shows the peak storm surge graphic. This provides a little more detail about how high the water levels could reach along the immediate coast. And this is generally kind of issued about 48 hours ahead of time. So this is, these values are valid out to about 48 hours of lead time. The values shown are above ground level, and the audience here would be a little bit different. This would be for people at the state level to kind of make decisions to use this type of information. And then the figure on the right provides even more detail. This is the potential storm surge flooding map, and what's depicted here is really what we call a reasonable worst case scenario. And this is based on the 10% exceedance output from our probabilistic guidance. So for a well-calibrated ensemble system, there'd be a 1 in 10 chance that these values would be exceeded. And again, the intended audience here would be state, county, or local decision makers. So all of these products are very important. There are different tools that we have available to us to communicate the hazards associated with storm surge. If you're interested in learning more about these products, I encourage you to listen to William Booth's talk from about a month ago. He also gave a CPAESS seminar where he goes into more detail on kind of the history of these products and why they're important. Today, though, I'm going to be talking about some of the model guidance that is used by the forecasters to create those products. These are example output. This is example output from probabilistic guidance for Hurricane Ian. This is what the fields would look like. So on the left is the probability of exceeding 6 feet above the NAVD88 datum. And this is at 48 hours prior to landfall. And then on the right, I'm showing the 10% exceedance values at the same time. So again, this is our reasonable worst case scenario. For a well-calibrated ensemble, you have a 1 in 10 chance of those values being exceeded. And you can see at this time, certainly the Southwest Florida coast was under the highest threat, but there was still some uncertainty as to the storm track. So probabilities were also higher north of the Tampa region. If you move forward to 18 hours prior to landfall, you can see that the probabilities have really increased in Southwest Florida, and highlighting the extreme risk there. And the 10% exceedance values have also increased dramatically. And this was a major event. Hurricane Ian claimed 41 lives to storm surge, and 36 of those alone were in the Fort Myers area in Lee County. So it was a really catastrophic event. So just to provide a little more background on the probabilistic model that we use, it's called P-Surge, and it's really just an ensemble of SLOSH model runs. SLOSH stands for the Sea, Lake, and Overland Surge from Hurricane model. And it's been around a long time. It's an older model, but it's very computationally efficient. And it does require an input wind field. And so one of the developers, in one of their papers said, that the wind model is just as important basically as the surge model. So if you want to have accurate surge forecasts, you need to have a good wind model. The P-Surge ensemble tries to account for uncertainty in the current forecast using historical errors from the NHC official forecast. And we try to account for errors in both the cross-track and a long-track dimension, and also in the intensity forecast. And we also try to account for uncertainty in the storm size. So I'll just provide a few more details about the P-Surge ensemble. We use 5 years of historical errors, and we have 3 different sets of errors that we use depending on the initial intensity of the storm. So errors if the storm is less than 50 knots intensity, and then 50 to 95 knots, and then greater than 95 knots. And we assume a normal error distribution, and we try to account for 90% of the historical error. So in the long track direction, we have 7 equally weighted members, and this is kind of to account for timing error in the track. And this becomes more important in the Northeast US, where you have larger tidal ranges. So you want to make sure that you're being able to capture like the storm surge as it phases with the different tidal ranges. We also try to account for uncertainty in the cross-track direction, and the number of cross-track members does vary, and it depends on the size of the storm at the 48-hour lead time. The cross-track spacing is set to be 1 RMW, or radius of maximum wind, apart. So if you have a very small storm in the official forecast, you'll have more cross-track members. We use a 3-member intensity ensemble, and so that we have like a weaker storm, a moderate storm, and then a strong storm. And you can see in this graphic here in the bottom left, we're sampling the 15th, 50th, and 85th percentile of the error distribution, and we create these representative storms based on the errors, again, assuming a normal error distribution. The middle member is assigned 40% of the weight, and then the 2 side members are assigned 30% of the weight. In terms of the RMW, I've got a little asterisk here beside that just because that has recently changed, and I'll go over those changes here in a minute. But previously, the RMW was determined based on the SLOSH parametric wind model, and it often didn't match with observations. We have a 3-member ensemble is generated based on the errors of holding those RMW values constant in time. All right, so just a few more points about the SLOSH hydrodynamic model that is, again, underlying the the P-surge ensemble. So this is the hydrodynamic model that we use. It's very computationally efficient, and it accounts for a lot of things. We even have a coupled wave model that we use for island regions like Puerto Rico, US Virgin Islands, and Hawaii, that accounts for wave setup, but it doesn't account for wave run-up or when waves are breaking near the coast. And it's not a total water prediction system. We don't account for river flow or rainfall. So certainly there's some limitations there. This figure here shows the basins. They're called SLOSH basins that we use for storm surge scenario planning. These are not the basins we would use in operations. Just because they're too large and they're too high resolution, they would take too long to run. We've got a different set of operational basins that run a little bit faster. All right, so I think it's important also to just kind of provide some information about how the storm size and structure are defined in the parametric wind models that we use. The top left here is a wind field from the SLOSH model for Hurricane Irma. And if you draw like a dashed line here out from the storm center out to the east, you can create a wind profile as a function of radius. And so the what we call the Rmax or the RMW is the radius at which the maximum winds occur. And that's a very important quantity for defining how a parametric wind field is, what structure it takes. Another thing we use are the wind radii. So this top right panel here shows the wind radii from Hurricane Ian prior to landfall. And these are basically the extent of the 34, 50, and 64 knot winds, and they can vary by quadrant. So you basically have 4 values for each of these wind speed thresholds. And if you look at in this idealized wind profile here, this is what the 3 different wind radii would look like. So there's a few different ways we can kind of define the size and structure for these parametric wind models. In the NHC official forecast, we do have wind radii information available if the intensity is above these thresholds. but they're not always available. 34 and 50 knot wind radii are available out to 120 hours lead time, but the 64 knot wind radii are only available out to 72-hour lead time. And I think it's important to understand that these parameters are used to sort of define the parametric wind models, but in reality, the wind structure can be a lot more complicated. So this is a SAR image showing the surface wind speed from Typhoon Sinlaku that just impacted Tinian and Saipan yesterday. And you can see that there's a lot more structure here that we're just not going to be able to capture in a parametric wind model. So RMW is very important for storm surge forecasting, not only in determining where the peak values occur, but also the amplitude or how much water is pushed inland. In this series of figures here, I'm going to kind of step through different RMW values, and you can see that the surge response increases dramatically as the RMW increases from 5 miles all the way up to 30-mile RMW. You can see that there's just a lot more water pushed inland. A real-world example of that was, again, from Hurricane Ian from 2022. And at the time that Ian made landfall, it had an RMW around 20 nautical miles. And the peak observations that, from Ian were above 12 feet above ground on Sanibel Island and Fort Myers Beach. And both of those locations were really close to the RMW for Ian. So if we go back to the SLOSH model, one of the challenges with the SLOSH model is that the RMW, based on the parametric wind model, often didn't match the best track values. So this is a time series of RMW from Hurricane Irma. The blue line is the best track, and the red line is the SLOSH RMW. And you can see that near landfall here, the SLOSH RMW was much too large, and this made it extremely challenging to use the guidance during Irma's landfall. And if you look at a number of cases, so this is the last 10 years of data, comparing the SLOSH RMW in red with the best track value, you can see that there's a poor agreement. They just don't match up very well. On top of that, the RMW forecasts that we used in PSurge are only a function of the initial RMW, and this is in version 2.7 and earlier. So on the left here, if you had an initial RMW of 15 miles, you would get you would generate an RMW ensemble that looks something like this as a function of lead time with the large, medium, and small member. However, if you had it started off with an initial RMW of 16 miles, so just a 1 mile difference, the evolution looked very different. And so these inconsistencies were really challenging, again, to use or to deal with during operational forecasting. So we went back and tried to create a climatology of RMW going back to 2001. And RMW is included in the best track, the NHC best track, but it's not a value that is QC'd to the same level as like the track intensity or the wind radii information. So there was some question as to how valid those entries in the best track really were. So we limited our sample to times when there was aircraft reconnaissance within, plus or minus 120 minutes. And you can see that the data set here, or the locations in our data set, are shown here on the left. The relationship between RMW and intensity is shown on the right from this data set. So as you get higher intensity, or for these stronger storms, the range in RMW collapses and you've got very small RMWs. But for tropical storm strength systems like 50 knots, you've got a lot of variance in the RMW. And these figures here on the bottom just show the relationship between intensity and RMW for a few cases. For Hurricane Matthew, there was a good correlation between RMW and intensity, but for Hurricane Jose, that correlation wasn't as strong. So there's other factors were affecting the RMW in this case. So we came up with a method to forecast RMW just using multiple linear regression based on NHC forecast parameters that are available in real time, such as the initial RMW estimate, the intensity, latitude, and then the average radius of the 34, 50, and 64 knot winds if they're available. And more information can be found in our paper from 2023 that describes this technique. But you might say, well, why not just use the RMW forecasts from like a global model like the GFS or a regional model like HWRF directly? And these are time series of RMW from Hurricane Zeta. And what's immediately apparent is that they're really quite noisy. They're also not going to be consistent with the official forecast. And from forecast cycle to forecast cycle, they're also not very consistent. So they're difficult to use in operations. And that's why using something that's regression-based, that's a little smoother, provides a more suitable solution for operational forecasting. So how do these RMW forecasts compare in terms of their skill? So the red line here is the previous version or previous method of determining the RMW based on the SLOSH parametric wind model. The blue line corresponds to when we start off with the initial RMW estimate, but then we use the same forecast methodology as before. And then the green line corresponds to these RMW forecasts that are regression-based and use the NHC forecast parameters as predictors. And you can see that in terms of the RMSE on the top panel here and the bias, they're making huge improvements, especially at longer lead times. So in order to incorporate these RMW forecasts into P-Surge, unlike intensity, we did not assume a normal error distribution. Instead, we used the cumulative distribution of errors. And directly from that, we were able to select the 15th, 50th, and 85th percentile to create or generate our ensemble members. But like intensity, we're also weighting them similarly, such that the center member receives 40% of the weight, and then the small and large storms receive 30% of the weight. We also have 3 different bins of error statistics based on the initial storm intensity. So that's similar to the other perturbations that we use in the ensemble. So here's an example figure showing the RMW ensemble for Hurricane Laura before it intensified. So on the left is the original method where the initial RMW really didn't match the best track value. And you can see that here at 48-hour lead time, it does a good job, but it's just sort of by chance. Versus using the RMW regression forecast, we do a much better job of encompassing the actual RMW for this case. In order to verify how well these RMW forecasts impact the P-Surge forecasts, we designed a retrospective database of storms that goes back to 2008. And now it includes storms out to 2024, Milton of 2024. Here are all the tracks from these storms. And for verifying P-Surge, we run up to 7 forecast cycles prior to landfall, starting at 72 hours prior to landfall. So there's about 280 forecasts that we run when we do a full set of P-Surge retrospectives. And so on the right here are the intensity and RMW values at the initial time to kind of give you an idea of what the characteristics of those storms are like. And so we've got a wide variety of different types of storms, some very strong, some weaker ones, and then some small storms and some very large ones. So, which is important when you're testing things to have a wide variety of cases. The observations we use come from NOAA co-op stations and USGS storm tide sensors, which are pre-deployed ahead of landfalling storms. So the figure here on the right shows all of the observations that we have available for these retrospective cases. And while it may seem like we have a lot of observations, again, this is for all 35 storms. For any one storm in particular, there are not very many observations. And often what happens is a storm will make landfall in between these sensors. And so it's difficult to record the peak values. And especially for the USGS sensors, those can fail during an event, or they may get washed away or not record the peak. So we always need more data. That's one of the challenges, I think, with verifying storm surge models, is just the lack of good observations. We are trying to objectively determine which observations to include in the verification. So we use a wind swath that's 1.5 times the radius of 34 knot winds to objectively select the observations. All right, so here are some results from these probabilistic runs. And these are rock curves. They essentially show the probability of detection on the y-axis against the false alarm rate on the x-axis. The colors are for the different lead times prior to landfall, and the little dots with numbers correspond to the exceedance thresholds. So here 0.1 would be the 10% exceedance. So again, for a well-calibrated ensemble, there would be a 1 in 10 chance that that value would be exceeded. And these are for probabilities of exceeding 6 feet above NAVD 88. The previous version of PSurge is shown on the left, and then the new version using the improved RMW regression forecast is shown on the right. So the zero skill line is shown in the black dash line. And ideally, you'd want to have curves that sort of extend up to the top left of this plot. And you can measure the skill based on the area under these curves. And so that's what's shown here, the AUC values. And I think the take home here is that these RMW regression forecasts improve at just about every lead time. And certainly at extended lead times, we have basically comparable skill to the old version at 48-hour lead time. So this is extremely important in that it helps extend the skillfulness of the guidance, which allows emergency managers and the public to have more time to make those important decisions related to evacuation. Just take a drink of water here. All right, so now I'm going to be talking about other shortcomings with the SLOSH model in terms of its wind field. And I want to highlight this by looking at a case, Hurricane Idalia from 2023. And these plots here show the probability of exceeding 6 feet above the NAVD 88 datum. And during this event, forecasters noticed that the probabilities in and around the Tampa area decreased quite a bit, from about 30% during advisory 12 here, which was 24 hours prior to landfall, to essentially zero in advisory 14, which was 12 hours prior to landfall. The actual storm tracked further north of Tampa, and those forecasts near the landfall location were, I would say, pretty good, pretty consistent. It made landfall near Steinhatchee, Florida. But certainly this area here near Tampa caught the eye of the forecasters. So if you look at the peak storm surge graphic for these three advisories, you can see that the forecasters really held the range of values pretty constant, from 4 to 7 feet to 4 to 6 feet at the advisories 13 and 14. So they really didn't change their strategy for messaging for this area. If you look at the East Bay tide station, which is in the Tampa area here. You can see that it was under a storm surge warning during this time. And in fact, this station did receive 4.5 feet above mean high water, which is about 5.4 feet NAV D88. So certainly there was a threat for storm surge, and this did verify. So we went back and kind of looked at what was causing the decrease in the probabilities for the Tampa area, and we ran a hindcast, just a single deterministic hindcast based on best track data. And if you look here at the hydrograph, you can see that the water levels in the SLOSH model really were way lower than what was observed at the East Bay station. Looking at the wind field, you can see that the extent of the 34-knot winds really didn't extend out very far from the storm center, certainly not over the Tampa area. So in order to get the water level values to match the observations, we had to fictitiously increase the radius of maximum winds for this case by quite a lot in order to extend the winds out past the Tampa area. And you can see then we get a pretty good match, but it obviously degraded the forecast for the actual landfall location. So we were just kind of curious what it would take to improve this forecast. So that kind of brings me to one of the other limitations of the SLOSH wind field, in that the winds are only a function of the intensity, or Vmax, and the RMW. And as a result, the winds are often too weak as you get away from the storm center. And because of that, because of this relationship, this simple relationship, it's not able to account for asymmetries in the wind field, where you might have stronger winds on the east side of the storm and really nothing in terms of significant winds on the west side of the storm. That often happens. Also, if you notice here near the RMW, you have a very broad area of peak winds, which doesn't look very realistic. So we've been experimenting with using the GTCM wind model, which stands for the Gridded Tropical Cyclone Forecast Advisory Message. And this is something being developed by Mark DiMaria and his team at CIRA, and it's used for other purposes in the Weather Service. But it's something we thought we should look into. It's based on a modified Rankine vortex, and the wind profile in each of the storm quadrants is fit to observations and forecasts. So you're able to kind of define the structure a little bit depending on the current conditions. And by nature, because of that, it's able to account for asymmetries in the wind field, and it just produces a more realistic looking wind structure. So returning to the Idalia example, here I'm showing the wind fields from SLOSH versus the GTCM, and then their difference on the right. The top panels correspond just to a particular time, and then the bottom panels show the maximum wind speeds throughout the whole simulation, but at hourly intervals. And so you can see in the SLOSH wind field here, the extent of the 34-knot winds, which is the green shading, really doesn't, it doesn't extend out very far at all. But in the GTCM wind model, you can see it does, and it covers the Tampa area and extends well inland over the Florida Peninsula. In terms of the surge response from these hindcasts using the SLOSH wind field and the GTCM, you can see there's a lot more water being pushed around in the GTCM using the GTCM wind model, especially in the Tampa area where we have around 4.5 feet above NAV D88 datum, versus in the SLOSH, there's almost really no water rise using the SLOSH wind field. So here's another example from Hurricane Irma. Irma was an extremely large storm from 2017. This little inset figure here shows the wind radii at just prior to Irma making landfall in Southwest Florida. And you can see the extent of the 34-knot winds basically covers almost the entire Florida Peninsula at this time. These profiles here, the solid lines correspond to the GTCM wind model, and the dashed lines are from the SLOSH wind model, and the colors represent the different quadrants of the storm, the green being the northeast quadrant, which was the largest at this time. And then these little colored dots correspond to the best track wind radii. And you can see that the GTCM wind profiles do a good job of being fit to the wind radii at this time. And it also captures the asymmetries in the wind field with the northeast quadrant being larger. On the other hand, the SLOSH wind field, the winds just drop off too quickly with radius. And again, you've got this very broad area of peak winds near the RMW. If you look at this in a 2D sense, the solid lines correspond to the best track wind radii. The dashed lines are from the SLOSH model on the left and the GTCM on the right. You can see the SLOSH wind field is just really way too small for Irma, but the GTCM does a good job of matching the best track structure. However, even though Irma was way too small in the SLOSH wind field, it's not always the case. There are cases like Ian from 2022 where the SLOSH wind field was actually larger than the GTCM. And so you can see that not only in the extent of the 34 knot winds here in the SLOSH model, but also the area of peak winds near the RMW was a lot larger than in the GTCM. In terms of the surge response in SLOSH, very high water levels throughout basically the entire southwest Florida coast. But in the GTCM, those water levels were a little more targeted in and around the Fort Myers area, which was a more accurate forecast. All right, so if we look at the wind radii and compare and contrast the GTCM wind model with the SLOSH, we can kind of get a sense of the general characteristics. So here I'm showing the average for R34, and this comes from our set of retrospective cases. So we've got 42 cases in this set. The black dashed line is the best track R34, the average for these 42 cases. The red is the GTCM and blue is for the SLOSH model. And you can see the SLOSH model has a small bias, especially in the northeast quadrant, which for a lot of cases is an important quadrant for storm surge forecasting. Looking at the right figure here, this shows the bias in the average R34 for all of these retrospective cases. And you can see that most of the SLOSH wind fields are too small, but the GTCM is a lot closer to that zero bias line. And looking at R50 and R64, for R50, both models do pretty well. SLOSH has a slight large bias in the southwest quadrant. And in terms of R64, the SLOSH model is a little large in all of the quadrants. It's likely because the intensity of some of our cases in the retrospective set is close to 64 knots. And again, you're kind of close to that area of very broad area of peak winds near the RMW that's affecting these results. All right, so we did have to do some tuning to the GTCM in order to improve it for SLOSH retrospective forecasts. We anchored the GTCM to the input RMW forecast that we provided instead of allowing the RMW to vary, which is sort of the default behavior. And that does help improve the fit of the wind radii observations, but we turned that off. We think that RMW is important for storm surge forecasting. And also, it's one of the dimensions that we perturb for the ensemble. So retaining that RMW is important. We're also fitting to the maximum extent of the wind radii versus a value that would be more representative of the average. So we're using the best track and official wind radii values directly. So here's an example of why this tuning is needed. So the blue curve here shows the RMW of the sort of GTCM before we've tuned that, and you can see it has a small bias in terms of the RMW, and the scatter plot here shows the same thing. So the tuning, this figure here shows kind of the example of how this tuning affects the wind field. These are radius time plots of the symmetric wind profile for Hurricane Helene from 2024. The black dashed line is the RMW, and then the blue, purple, and red lines correspond to the 64, 50, and 34 knot wind radii from the best track. So ideally, you'd want to see like the extent of the green shading to kind of match up with the red lines here. In the default GTCM, you can see the peak winds occur inside the RMW at just about all lead times. And then after we've tuned the GTCM, you can see that those peak winds occur right at the RMW. However, in this case, the fit for the 64 and 50 knot wind radii is a little bit worse compared to the default GTCM. And again, that's just one of the compromises when you anchor to the input RMW. All right, so how does the verification look? These are from deterministic hindcasts using the SLOSH wind field on the left and the GTCM wind field on the right. And you can see that we've improved the RMSE from 2.26 feet to 1.78 feet, and also reduced the negative bias from negative 0.81 feet to negative 0.35 feet. So certainly making some improvements in terms of these deterministic forecasts. If we look at the RMSE on a case-by-case basis, a few storms kind of stand out. Ian is one where the RMSE has decreased from 5 feet to 2 feet. So there were big improvements for Ian. However, there are still a few cases where the SLOSH wind field produces better results, like for Ike and Sandy, and those are cases we're looking into to try to figure out why that is. So because these deterministic verification results were positive, wanted to use the GTCM or try using it in the probabilistic guidance in PSurge. But again, the GTCM requires wind radii information. So we had to do some work in order to produce those or to get that information. And here I'll just kind of show why that's necessary. So if you look at these idealized plots of the RMW ensemble on the top left and the intensity ensemble on the bottom left, you can see that when you increase the RMW, the R34 also needs to be adjusted here. It becomes larger when the RMW increases. And likewise for intensity, as you increase the intensity in the ensemble, the R34 also increases. And this becomes even more important for ensemble members where both the intensity and the RMW are perturbed. So here the red dashed line corresponds to the large, strong member, and the blue dashed line is the weak, small member. And you can see there's a big difference in the radius of 34 knot winds. So we had to develop a methodology to forecast the average R34. And again, we're using NHC forecast parameters, latitude, intensity, RMW, and the initial R34 when it's available. We are not making, at this time, we're not making adjustments to R50 and R64 just because that adds a lot of complication. And initial testing revealed that as long as we anchor to the RMW and R34, the results are pretty good. So that might be something we explore down the road. But right now, we're just starting with R34. And these are the regression verification of those regression forecasts of average R34 compared to the official shown in black. And the red line is where you have an initial R34, and the blue line is when you don't. So the initial intensity would be below 34 knot winds. So this was encouraging, and it suggested we could use this technique to provide the wind radii information to the PSurge ensemble. So here's an example from Hurricane Milton from 2024 showing the track ensemble and then the RMW and intensity ensemble members at this time. And we generated R34 forecasts for those Vmax and RMW ensemble members. And those are shown by the red, green, and blue lines here. And at this point, they're all centered around the average R34 forecast for the unperturbed member. The pink line here is the average R34 that comes out of the official wind radii forecast. So you can see, ideally, we want to have these average R34 forecasts centered in reality. So we end up shifting the distribution so that they're centered on the official forecast, as shown here in the bottom right figure. The other thing we try to do is we look at the structure in the official forecast, and we notice here that the northeast quadrant is a little bit larger than the other quadrants. So we try to take that into account and apply these asymmetry factors to the R34 forecast for these perturbed members. So you can see that's reflected in the resulting R34 distribution. And here the blue dashed line would correspond to the average R34 forecast for the large, strong member. And the red dashed line here corresponds to that forecast for the small, weak member. All right, so after we made these adjustments and we accounted for the wind radii information, we ran a set of P-surge probabilistic experiments. And here are the results. Again, these are looking at the verification in the rock curve space. So a higher area under the curve is better. And you can see that while the GTCM has close values to the original SLOSH wind field, the SLOSH wind field produces higher values of area under the curve, except maybe at 60-hour lead time. I'm not sure whether these values are significantly different. Perhaps at 12 and 60 hours they are, but certainly we have some more work to do. These are fairly recent results. And if you notice here, really what's different about this is that the GTCM has a slightly lower probability of detection, but it does have a slightly better false alarm rate. So we have some ideas of what we can do to try to improve these results. All right, so I will just provide a few summary points here quickly to wrap up. Again, the RMW that's available in the SLOSH parametric wind profile was often inconsistent with observations. So we developed a technique to predict the RMW, and those really showed improvements in terms of the probabilistic verification in P-surge. Looking at the overall structure of the SLOSH wind field, it's often too weak as you get away from the storm. The R34 is too small, and this is important for cases like Idalia. And the GTCM wind field just does a better job of fitting the wind field to what the observations suggest. So we've tuned the GTCM a little bit to try to improve the SLOSH deterministic forecasts. And if you compare the GTCM with SLOSH for these hindcasts, there's a big improvement. And in order to use the GTCM in P-surge, we had to develop a method to provide regression forecasts of the average 34 knot winds for these perturbed Vmax and RMW ensemble members. And the initial evaluation is that the probability of detection needs to be improved using the GTCM wind model when we're using P-surge. So that's work that's currently ongoing, and hopefully we can kind of overcome that challenge. All right, so just to kind of wrap up, I wanted to revisit this example from Hurricane Idalia, where the forecasters noticed the probabilities of exceeding 6 feet above datum rapidly decrease over this set of advisories. And thankfully, they understood the nuances and that this area was susceptible to storm surge. They used their experience and knowledge to hold fast in their forecasting, how the risk was being communicated to the public. But I couldn't help but wonder, what would have happened if forecasters had changed their forecast based on the guidance that was available to them. And I think it would have put the National Hurricane Center in a bad position, and ultimately, might have put a lot of people in harm's way in this area. So I think we, obviously we want to try to work towards a point where the forecasters can trust the guidance. And when they see changes like this, they're not always having to second guess the guidance and what's going on. So that's something we're obviously striving for. And, the other point is that as the forecasts from the NHC Hurricane Specialist Unit continue to improve in both track and intensity, without making simultaneous improvements to the wind model and the storm surge, framework, cases like Idalia will continue to be challenging. Because even if you had a perfect forecast, both in track and intensity, even though the storm surge forecast near the landfall location might be improved, we would still have gaps in the guidance for areas like Tampa here. So this just highlights kind of the importance of why these improvements are necessary. And with that, I'm happy to take any questions that people might have.
Thank you very much for sharing your work with us, Andy. It was truly fascinating. We can now start our Q&A portion of the seminar, and I want to direct your attention again to Slido to ask your questions. Remember, it is on the tab on the left. Or you should have a QR code that is going to pop up on your screen momentarily that you can also use. While all of that is going on in the background, I would like to invite you to check out our website, CPAESS at UCAR.CPAESS, for all our upcoming seminars. Our next scheduled seminar is on Wednesday, May 20th at 11 a.m. Mountain Time, and that will be with Yao-Wei Lee, one of our Climate and Global Change postdoctoral fellows. And he will be speaking on From Regional to Global, the far-reaching impacts of wildfire on the atmosphere and climate. I also invite you to look at our CPAESS YouTube channel for all our past talks, as well as this talk once it is available. So with that, let's move over to questions.
Our first question is from Lynn, who asks, the use of artificial intelligence is rapidly expanding, especially in science-related fields. How do you envision AI impacting storm surge forecastings and what you do?
Yeah, that's a good question. I think AI is everywhere now, and I think it will likely heavily impact what we do at the storm surge unit. I think there's probably a spectrum of ways that it could be used, from simple post-processing the results to kind of make the ensemble a little more reliable. I think there's some space for that. One thing that we're looking at is the possibility of using AI ensemble information to kind of constrain our uncertainty in certain respects. So, for example, if you had a particular forecast where the track forecast was very certain, we knew where the storm was going to go, but we didn't know how strong it would be. So in that case, maybe you don't use as many ensemble members to account for uncertainty in the track, but you add members to the intensity portion of that ensemble, try to account for that. So I think there's, something that we could be leveraged there. And ultimately, I think probably it won't be too long before there's really an end-to-end solution using AI techniques to predict, the total water level from storm surge. So I think that's probably coming.
Looks like we have another question from Andy. Thanks for the interesting presentation. I have a detailed question. On applying the sampled errors from different quantiles, for example, 0.85, and as he said it's around slide 8, are the sampled error quantiles applied to every time step of the forecast and location identically, assuming I'm interpreting this correctly?
Yeah, they are. So if we're using the 85th percentile of the errors to kind of define either the strong ensemble member or the large ensemble member in terms of the radius of maximum winds, those are applied at every forecast hour. And they depend on the initial intensity of the storm. So right now we're using different error sets for what we call kind of like tropical storms. And then we've got sort of, medium intensity hurricanes and then strong hurricanes. We have different error statistics for all three of those sets.
Excellent. Sue asks, what do you think are next steps in research to continue to improve storm surge forecasts?
Yeah, I mean, I think there's a lot of different avenues for improving the forecasts. I mean, ultimately, I think we're sort of at the mercy for good track and intensity forecasts, but I think, like areas like what I shared today with improving the wind structure, I think that's something that, there can be a lot of work done. We're somewhat tied to using a parametric wind model just because, if we're running thousands of ensemble members, it makes it difficult to account for more structure in the wind field. And in a probabilistic sense, it's not clear whether that extra structure or all those little nuances accounting for that will really help either. So we're somewhat tied to that. And then obviously I think, defining kind of more like in the hydrodynamic model, how far inland does the water get pushed? And so, that's a difficult thing to understand and to understand like if we're making improvements even, because we just don't have many observations. So I think, there's a huge gap in terms of our ability to even observe these events adequately to understand when we're making improvements. So there's a lot that can be done, I think, to improve.
Thanks for that. And if anybody have additional questions, please do post them. We have about a minute or two, so we are running very short on time here, but I'm sure we can squeeze one in. Or you are also very welcome to reach out to Andy afterwards and discuss this work with him. Not seeing additional questions at this time, I do want to thank you all for coming to our CPAESS Discovery Seminar Series. And remember, you can visit our website at cpaess.ucar.edu to find more about this talk as well as future talk. And at that website, you will also find a link to past talks once they are uploaded and a link to our YouTube site. And with that, Andrew, I want to sincerely thank you for sharing your important work with us today. Thank you for our CPAESS staff that made this possible and working in the background, Don Mullally and Alex Mayer, along with Chris Sepp and Paul Martinez from our UCAR Multimedia Service for their invaluable assistance in making this seminar work. And I do hope to see you all at our next CPAESS Discovery series. And have a good afternoon, everyone.
Thanks.